In this video, we'll be covering the root test. The root test, very much like that of the ratio test, has a restriction on what the terms can be inside here. So we're going to go ahead and let this be an infinite series, except for instead of it having positive terms like that of the ratio test, it's going to have non-negative terms. So in this case, the root test modifies its conclusion or statements because non-negative terms based on the radical. Again, it's a root test, so we're going to take a radical. So then we're going to go ahead and look at this thing called rho, and we're going to go ahead and denote that rho as the limit as k goes to infinity of the kth root of a sub k. So unlike that in the ratio test, where we're going to go ahead and compare the term to the next term in a ratio format, again, that's why it had to be positive and not zero. It couldn't be zero terms. And this one's just referring to non-negative terms because it could still be zero. I could have a zero inside this radical. So with that being said, we have three conclusions, and these conclusions are actually identical in concept to the ratio test. Those three conclusions are: if I have 0, p or rho is less than or equal to, greater than or equal to 0 but less than 1, then the series will converge. If I have p or rho, again, is greater than 1, then the series a sub k will diverge. And then if rho is equal to 1, just like that, again, we have the test is inconclusive. So again, if you recall the workings of the ratio test, it was the exact same statements and exact same rules. The only difference was that in the ratio test we had positive terms as opposed to non-negative terms, which isn't that really of a drastic change. Again, the proof for this is relatively complex and more difficult to show than the ratio test proof. So we're going to bypass the proof on how this is true, and we're just going to jump straight into utilizing it. Now, the root test in terms of the use of it is going to start with examples that look like this. So k equals 1 to infinity of some obnoxious looking thing as a function all to the power of k. And you're looking at this going, well, this looks like it should obviously be applied to the root test, specifically because, well, that power of k. So, and the inside is also not just a number. If the inside was just a number, then we could talk about this being a geometric series and be done with it. But it's not a geometric series. It's got some other stuff that's going on inside of it. So with the fact that it's got other stuff going on inside of it, we're going to go ahead and apply the root test. So the root test, again, specifically says that I'm going to take the sequence that's in here. This stuff in here is really my a sub k. I'm going to take the limit as k goes to infinity of the kth root of that thing, so 4k squared minus 3 over 7k squared plus 6, all to the power of k. And we're just going to go ahead and evaluate this as though it's just some basic limit. In this case, I'm going to have the limit as k goes to infinity of, it's going to end up being 4k squared minus 3 over 7k squared plus 6. Sorry, is that 6? Yes, that's 6. And then we can do one of two things. We can apply L'Hopital's rule with the fact that this goes to infinity on top and this goes to infinity on the bottom. Or we can choose to multiply by 1 over k to the power of 2, the largest power of k in the denominator, on top and on bottom. Distributing that through provides me with the limit as k goes to infinity of 4 minus 3 over k squared, divided by 7 plus 6 over k squared, and therefore this provides me with a value of 4 over 7. Now let's return one more time to the definition of the root test. If we have a value that's between 0 and 1, then the series will converge. If we have a value that's greater than 1, then the series will diverge, or that if it's equal to 1, then the test is inconclusive. So in this particular case, I'm getting a value that's less than 1, so I can state that by the root test, with rho equaling to 4/7, the original series of 4k squared minus 3 over 7k squared plus 6 all to the power of k is convergent. Looking at another example, the series of k equals 1 to infinity of 2 to the power of k divided by k to the power of 10. So now the difference between this example and the previous example is that this example doesn't have everything to the power of k. But the fact that it's got enough stuff to the power of k will give us some kind of mentality that we could potentially attempt to use the root test. It is also possible, a viable option, to attempt to use the ratio test on this. but there might be some conclusionary issues that can cause problems. So let's go ahead and start with this thing right here, and let's go ahead and work with the rho is equal to the limit as k goes to infinity of your kth root of the entire thing, so 2 to the power of k divided by k to the power of 10. If I simplify this a little bit, I'm going to have limit as k goes to infinity of, I can distribute radicals over division, so this will become 2 on top, because the kth root of k, something to the power of k, is just going to be the base. And then on the bottom, I'm going to have k to the power of 10, technically the power of 1 over k. So this is really equal to the limit as k goes to infinity of 2 divided by k to the power of 10 over k. And the tricky part here is to come up with a way that can very easily or appropriately conclude what this thing is convergent to. What I'm going to do one more step is the limit as k goes to infinity of 2 over k to the power of 1 over k. So just like I took this 1/k and I pulled it in, I'm actually going to pull the 10 out so that it looks like this. And then I'm going to deal with what is the limit as k goes to infinity of k to the power of 1 over k. The reason why I'm going to tear this apart is because if I can evaluate this piece right here, then I know what this piece does to the power of 10. If this piece right here goes to, say, 5, well, then it's 5 to the power of 10, and I'm done. The fact that these two pieces are constants actually make the evaluation of this limit relatively straightforward. So just like we did in the previous video for the ratio test, we said, well, let's take a look at this thing as though it's y equals. Again, when I have a power to an ugly power in terms of them all being some kind of manipulation of k, then I'm going to work through those problems utilizing that function of y equals such that I can take the natural log of both sides. This one's actually a little bit easier to handle. I'm going to take the natural log of both sides. I will show all these individual steps such that I pull the 1 over k power down in front, so I have the natural log of y is equal to 1k natural log of k. This becomes the natural log of k over top of k, and then if I take the limit as k goes to infinity of the natural log of k over k, this is supposed to be equal to the limit as k goes to infinity of the natural log of y, then I should be able to conclude that whatever this thing does, the natural log of y will also be equal to that thing underneath the limit. So this thing goes to infinity over infinity, which means that I can apply L'Hopital's rule. Under L'Hopital's rule, I get that this is 1 over k, the limit as k goes to infinity of 1 over k divided by 1. The derivative of the natural log of k is 1 over k. The derivative of k is simply 1. And this thing then goes to the limit as k goes to infinity of 1 over k, which is 0. So now I have the natural log of y inside of that limit equals to 0. So that means that y is equal to e to the 0. And if y is equal to e to the 0 within that limit as k goes to infinity, then I'm going to go ahead and backtrack all of this work up to here. This thing is really equal to e to the power of 0, which is 1. Now again, the difference between this and previous examples is that the limit as k goes to infinity of 2 is 2. The limit as k goes to infinity of this function is this thing which goes to 1 to the power of 10. And the reason why this is acceptable to do is because this piece is the only thing changing, and it's getting closer and closer to 1, while this 10 power is not changing. So 1 to the power of 10 is 1, mainly because the fact that this 10 is not changing. If that 10 was changing, it'd be an entirely different story. So this thing is equal to 2. And let's recall by the root test, if I take the limit of the kth root of this function, and I get something larger than 1, then the original series here will diverge. So then, by the root test, therefore, by the root test, with rho equal to 2, the series 2 to the power of k over k to the power of 10 is divergent.